Good morning. Thank you for being here. My name is Omar Rojas Bolaños, and my coworker is Alejandro Delgado Castro. We are lecturers and researchers at Universidad de Costa Rica, Campus Guanacaste. Today, I would like to share with you our preliminary results of our research. We are interested in using computational strategies to reduce the noise levels in cyclic voltammograms of manganese dioxide using a low-cost potentiostat. Manganese dioxide has been used in the construction of supercapacitors and other energy-related applications. And this compound can be produced in the laboratory by means of an electrode deposition over thin stainless steel strips. Once produced, these compounds can be characterized by different techniques, such as cyclic voltammetry. Obviously, these methods require the use of one potentiostat. And in this point, it's important to say that the price of professional potentiostat can be a restrictive factor for some educational institutions. Because of that, we are interested in low-cost potentiostat. In the last years, different designs have been proposed, and many of them have been based on Arduino Uno boards. An Arduino Uno is a programmable circuit board designed to build in interactive electronic projects. This is an open source platform, so it's very popular among students and hobbyists and scientists. Some years ago, Meloni presented an initial simple design based on several voltage sources and the Arduino Uno board. And some months after Meloni, Lee and others presented another design called Huami potentiostat, based on a single power source and control from Arduino Uno. They also provided an interface in LabVIEW for the computer. And some years ago too, we proposed our potentiostat. And this is the circuit of this potentiostat. It uses a single power supply and is controlled from the computer via the Arduino Uno board. And in this model, the voltage of the reference electrode follows the input voltage, which is a filtered PWM signal generated by the Arduino Uno and controlled by the user. Also, in this model, the voltage in the terminals A0 and A1 are used to calculate the voltage, or the cell voltage, and the current of the cell, respectively. And in my opinion, this approach is easier to understand. In this picture, you can see part of our system. Here is the control circuit of the potentiostat that was assembled in a breadboard, on a breadboard, sorry. And here you can see the Arduino Uno board. And these three wires correspond to working electrode, reference electrode, and counter electrode. In previous work, a set of equations was deduced, and it can be used to operate the system during an electrochemical experiment. Okay, the first step in our work was the electrodeposition of the manganese dioxide. It is conducted by chronon pyrometry using a 0.2 molar per liter manganese 2 sulfate solution in this electrochemical cell. A stainless steel strip, this one, is used as working electrode, and a lapse cupola acts as a counter electrode. And the reference electrode is a silver chloride electrode with 1 molar per liter potassium chloride filling solution. A constant voltage of 1 volt is applied to the electrochemical cell using the professional potentiostat Palm Sense 4. And following this method, it is possible to obtain films of manganese dioxide. And these films look like this. These films were obtained with different equipment. And if the color is darker, the amount of manganese dioxide deposited is bigger. And after obtaining the manganese dioxide films, then each deposit is analyzed by means of cyclic voltammetry, using the professional equipment and the proposed potentiostat. And the experimental parameters that we used were initial voltage, 0.4 volt, switching voltage, 0.8 volt, final voltage, 0.4 volt. We used a voltage scan rate of 10 millivolts per second and 15 cycles. In this picture, you can see the behavior of the voltage in different parts of the circuit. In color, in blue, you can see the input voltage, and in green, you can see the voltage of the reference electrode. In this picture, it's easier to realize that the voltage of the reference electrode follows the input voltage. And in purple, you can see the voltage in the terminal A1. This voltage is related to the current of the cell.
Thank you. As my colleague Omar has just explained, during the cyclic voltammetry, the voltage applied to the electrochemical cell is changed gradually during time. And to do that, we use a PWM signal with different widths in every time interval. And in every step, or for every week for every step of the PWM signal, we have to measure the current that is flowing through the electrochemical cell. Currently, we are taking 60 values per width of the PWM signal, and in this picture, we are showing some of these values for one particular width of the signal. And as you can see, the variation in these measurements can be quite significant. For instance, in this case, we're measuring currents ranging from minus 2.4 milliamperes up to 2 milliamperes. And trying to estimate the true value of the current that is flowing through the electrochemical cell is quite challenging. So we are now using or trying to use computational strategies to filter or to estimate the true value of the current that is flowing through the electrochemical cell. In this case, we're using MATLAB to apply 5 computational strategies to this data in order to see if we can reduce the measurement noise. And in this case, in these figures, we're presenting the voltammograms obtained during the tests. On the left, we can see the voltammogram that was obtained using the PalmSense 4, the professional potentiostat. And here you can see the clean and very nice pseudo-rectangular shape of the voltammogram that is associated with the pseudo-capacitant properties of the manganese dioxide. On the right, you can see the voltammogram that was obtained during the lower cost potentiostat that we are developing. There is a clear shape, a similar shape of the pseudo-rectangular voltammogram that we obtained, but obviously there are a significant amount of noise in this data. In this case, we took the mean value of the 60 values of current that was measured during every width of the PWM signal, but still we have lots of noise present in our voltammograms. So in the next step, we tried changing the set of data that in which we were applying the mean value. On the right, on the left figure, we decided to use the 30 initial values of current that were measured in every width of the PWM signal. And the consequences of doing that is an increased maximum and minimum average currents during in the voltammograms. And on the right, we decided to use the 30 last values of the set of 60 measurements. And as you can see, the shape of the voltammogram was shrunk by some margin, and the noise levels were also increased. So as a fourth measure, we decided to apply a 10th order moving average filter to the entire set of 60 current measurements in order to see if we can reduce the noise levels. And as you can see, the shape is very similar to the initial that we showed, and the filter just has a very little impact on the levels of noise reported. And also on the right, we decided to try a 5th order median filter on this very same set of 60 values to see if we can reduce these levels. But as you can see, the noise levels were indeed increased. So as conclusions for our work, we could see that neither of the computational strategies applied so far was able to generate a clean voltammogram such as the one that was obtained with the professional PalmSense 4 potentiostat. Obviously, we are not including any particular circuitry in our hardware to deal with these noise levels. So the voltammograms showing the lowest levels of noise were generated by taking the average of the entire set of 60 current measurements, or eventually using the 10th order moving average filter. For future work, we would like to try some additional alternatives. For instance, we will try to create a PCB, a printed circuit board, for the control circuit that we're using in order to reduce the noise sources that are coming eventually from the hardware. And we would like to use also a different feedback resistor that is being used in the current measurement system. And we think that we can increase the accuracy of the system by increasing the resistor in this feedback loop. And also we would like to consider or taking additional measurements of current per each width of the PWM signal. And to conclude our talk, these are the preliminary results we wanted to share with you this morning, and we would be very happy to address any question or additional comments you might have. And thank you very much for the attention.
Thank you very much for the nice talk. Any questions? Comments? Edgar?
Hello, thank you very much for this very nice talk. And do you happen to have like a figure with the CV, both the one taken with the professional equipment and yours, just to see what they look like, how alike they are, or something?
A picture showing the
Like
professional
both
equipment?
both CVs in the same plot, just to see if they look how similar they are or something.
The voltammograms?
Yeah.
All right. Yep. So the one on the left here is the one that we obtained with the professional equipment. And as you can see, the average current during one of the sections of the voltammogram is around 300 microamps, whilst the negative one is around minus 300 microamperes.
Yeah.
On the right, this is one of the best that we have obtained with the current state of the equipment. We are basically obtaining very similar ranges of current during the test. The problem is basically the noise that we have in every point.
And these are, this is for the very same sample or for two slightly different samples, or?
They were two samples obtained with,
Two different
created
samples.
using
Okay.
the palm sense for a potentiostat for the electrode deposition.
Okay.
Yep.
One more question. Thank you.
Hello. One question regarding the microcontrollers.
Yep.
Why did you choose the Arduino Uno, and do you have in mind any other microcontroller that could work in here with different specs?
Well, basically the popularity and the price. This is one of the cheapest versions in the market. So we wanted to know how much we can squeeze out from this very cheap equipment.
Okay.
Obviously, there are more sophisticated alternatives, but we just wanted to try the cheapest one first to see how much accuracy we can get out of the controller. Yeah.
Okay, perfect. Thank you.
Yeah, too.
We have time for one more question. Okay, if not, speakers again.
Thank you very much.
So this concludes the morning session. I want to first of all thank all the speakers for the very nice talks that they presented today. So let's thank them again. And now lunch will be served in the next room where the coffee was served. And the afternoon session starts at 1:30, so please be here by 1:30, okay?